Hello everyone, welcome to Technologies Discussion channel. Today, I'd like to start a new topic of discussion which is on filter design. Okay, so for the first few series discussion on filter design, I'm going to explain the different filter terminologies and also the key parameters to decide the spec of the filter. This video, basically I will go through the four types of microwave filter. So there are actually four types. The first one will be low pass filter. Second one will be high pass filter. Third one will be band pass filter. And last but not least, band stop, or sometimes they actually known as band reject filter. So this will be the part one series discussion on filter design. So guys, if you're keen to know more about filter design, please take a look on the playlist under the description. Over there, you will be able to find a series of discussion on filter design. This is my email. If you have any question regards on this discussion, please drop me an email. Or if not, if you want to have a faster response, you are also welcome to ask me your question through the comment. I also seek the help from the expert here. So basically, if you have anything to contribute on filter design, please contribute through the comment. Please help this learning committee to learn more about filter design. Before I continue, I'd like to urge you guys to help this channel by like this video. For those who are new to this channel, please consider to subscribe and turn on your notification bell. Once again, thank you so much for your strong support. Let's quickly understand what are the role of filter. In fact, filter play a critical role in many RF or microwave application, where they are actually used to separate or maybe combine different frequency. Given the limited nature of the EM spectrum, we know that this electromagnetic spectrum, they are actually limited. So basically they are resource. So therefore, this resource must be cleverly shared by all. So hence because of this, filters become an essential for us to select or even to confine our own signal within the design spectrum limit. Emerging applications such as wireless communication impose increasing stringent requirement on RF microwave filter, demanding high performance such as low insertion loss, small size, compact, lightweight, and even low cost, depending on specific requirements and also the specification. RF microwave filter can be designed either as a lump element, LC element, or nowadays, this is actually more popular as a distribute element circuit. They may also be implemented using various transmission line structure, including waveguide, coaxial, and microstrip, which I'm going to describe at the end of this video. What is actually a filter? RF or microwave filter, they actually represent a class of electronics filter designed to operate on signal in the mega to the gigahertz frequency band. So basically this is the band for RF or maybe microwave. So basically they work in the frequency range of mega all the way to gigahertz, which is the medium frequency all the way to the extreme high frequency. These components are used in electronic system to pass or reject specific frequency and antenna unwanted signal within the microwave and RF range. So I will explain this based on the four types of filter. This frequency range is commonly used by most broadcast, radio, television, and also wireless communication systems such as cellular phone, Wi-Fi, etc. As a result, most RF and microwave devices actually include some form of filtering for the signal they actually transmit or receive. Such filters are often used as building blocks for duplexers, and also the duplexers enable the combination or separation of multiple frequency band. So these will be the key parameters that I will firstly discuss on the first few series discussion on filter design. So this video, I will concentrate on the type of filter. We have low pass, high pass, band pass, and band stop filter. The next video, I will explain what is actually the center frequency and also cutoff frequency. Maybe in this video, I will also briefly explain what is actually the center frequency and also the cutoff frequency. The fourth one will be the so-called the Q factor or the selectivity factor. Okay, we call this high Q or low Q. Okay, high Q means narrow band, low Q means wide band. Okay, so basically this is what we mean by Q of band pass filter. Next will be the shape factor. Okay, shape factor is actually stop band over pass band. Okay, so basically this is to quantify okay how much so-called bandwidth etc. will be utilized as a filter. Next will be insertion loss. Okay, so insertion loss is basically the pass band, how much you actually lost because they actually went through this filter. Okay, so basically, for example, for the band pass filter, under the pass band, we want to have as little insertion loss as possible. Okay, so basically, this is insertion loss. VSWR or return loss. So basically, this is S11. Okay, so basically, you can see that when they actually match, all the signal will be able to pass. For example, for this case here, we want it to be a pass band. For this case here, probably we want it to be a so-called a band reject, and therefore some of the signal actually reflected back. So this gives you some idea what is VSWR and return loss. Phase linearity. Okay, for example, you have an input signal here. When they go through the filter, okay, so basically there will be a change of phase. Basically, this phase linearity will determine how much phase difference when they are actually at the input as compared to the output. Group delay, okay, which means that again, when you actually pass any component, you bound to have some delay. Okay, so basically this group delay is how much delay, okay, when I actually pass through this filter network. Okay, so in short, the lesser the delay, the ideal will be the filter. Last but not least, on the filter impedance, we have the input and output impedance. Okay, so we need to determine this so as to do a so-called perfect match on this filter network here. So basically, these few 9 key parameters, okay, which I will discuss on the first few series discussion on filter design. Okay, let's quickly go through the discussion for today. First, which is the types of filter. Okay, as I mentioned earlier on, there are actually 4 types of filter. Okay, so this is the frequency response. Okay, which means that this is the frequency and this is the S21. Okay, you can imagine that these are all S21 here. So from here, you can see that we actually have 4 types. First one is actually the low pass filter. The second will be the high pass filter. The third will be band pass filter. And last but not least, band stop or band reject filter. Okay, on my next slide, I will give more comprehensive discussion on these 4 types of filter. Okay, let's start by discussing the low pass filter. Okay, low pass filter actually allow low frequency signal without any attenuation. Okay, in the ideal world, decrease in power, okay, but it actually reject any high frequency signal. So what does this mean? You can see that this is actually the frequency response of a low pass filter. You can see that this is from low frequency all the way to high frequency. From here, you can see that the low frequency, they actually fall under this pass band, which means that all the low frequency will be able to pass. When higher frequency, okay, which means that when they are actually more than the cutoff frequency, then they will fall into stop band. From here, you can see that all the high frequency will be stopped. So from here, you can conclude that low frequency can pass, high frequency will be stopped. So hence, we call this low pass filter. The same philosophy can be applied for this high pass filter. You can see that at low frequency, okay, they cannot be passed because they fall under this stop band, while at high frequency, they will be able to pass, which is called this high pass filter. Okay, you can see that higher frequency, they actually fall under this pass band here. So high pass filter is actually they allow high frequency signal to pass without any attenuation in its amplitude, and they actually block or reject any low frequency signal. And hence, because of this, this is actually called a high pass filter, as you can see from here. Okay, so the next one, okay, will be a band pass filter. Okay, so this type of filter actually allows a specific band of frequency and block any other frequency lower or higher than its pass band. Okay, so this is the frequency response for a band pass filter. Okay, from here you can see that we actually specify the band, okay, which is F1 to F2. So basically the band F1 to F2 will be able to pass the rest will be rejected. So basically from here you can see that we actually specified the band to pass and the rest will be rejected. So hence because of this, this is actually known as band pass filter. Last but not least, on band stop or band reject filter. Okay, so this type of filter actually attenuate the signal, okay, whose frequency lie in the fixed band of frequency. Okay, over here you can see that, for example, I actually customize the design that actually I want to stop this band here. So basically you can see that this band will be stopped, the rest will be able to pass. So from here you can see that we actually design this filter, okay, to stop the frequency at the interest, okay, frequency. So therefore, this form here, we call this either band stop or band reject filter. Okay, so from here, I hope you have some idea, okay, what are the types of filter. Okay, let me continue. Okay, so basically, this is what we call an ideal filter. Okay, so basically, ideal means that you can instantly change from pass band all the way to stop band. Okay, so this is what I mean instantly. Okay, but in the reality world, you can see over here, you actually require some time to transit from pass band to stop band. Basically, this will be the transition time. Okay, but okay, ideal, okay, basically will be easier for us to understand the characteristics of filter. Okay, again, from here you can see that this form is actually a low pass filter. This form is actually a high pass filter. This form is actually a band pass filter. This form is actually a band stop filter. Okay, so before I continue to give you an example, okay, how can we actually understand better based on this four type of filter? Okay, I'd like to urge you guys, if you have learned something, please help to like this video. Okay, when more of you guys actually like this video will have a better chance to reach up to a larger audience. So guys, help me by like this video. Okay, for those who have learned something, again, you are new to this channel, please consider to subscribe and turn on your notification bell. Let's continue with the example. Okay, so basically this is the example that I'm going to do it together with you guys. The diagram below actually show the response of four filter. Okay, so basically this is low pass, high pass, band pass, and band stop here. Okay, so basically this is the first task that which I have already done. Okay, state the type of filter for each response. Okay, so basically a signal consists of four frequency component, 10, 20, 30, and 40 kilohertz is fed into these four types of filter. Okay, so we need to draw the frequency component that will be appeared at the filter output. Okay, so how can we start this? Okay, so basically this is what it means here. So basically there are actually signal at 10, 20, 30, and 40 kilohertz here. So this is what it means here. We actually have four frequency component at this four different frequency, which is drawn over here. So this signal, for example, is actually fit into this low pass filter. You can see that the cutoff frequency for this low pass filter is actually at 25. Okay, so how can we know which one will be able to pass? So basically, you correlate these two diagrams into one, as you can see from here. These two diagrams you draw into one. So from here, you can see that this is actually pass, and this is actually stop. So after they go through the band pass filter, you are quite sure that only the frequency at 10 kilohertz and 20 kilohertz will be able to pass, while the signal at 30 and 40 will be rejected by this low pass filter. Can you double confirm here? You can see that all the low frequency can pass, while the higher frequency will be rejected. So therefore, this is what we call a low pass filter. Okay, so next, with the same four types of signal here, okay, so now we are going to feed into a high pass filter. You can see that this high pass filter has a cutoff frequency at 15 kilohertz. Again, if you put these two diagrams into one, you can see that they have this kind of characteristics here. So you can see that this will be reject, this three will be able to pass. So finally, at the output of this high pass filter, I will actually have 20 kilohertz, 30 kilohertz, and also 40 kilohertz, while the only one that will be rejected will be 10 kilohertz. So again, from here, you can see that all the high frequency component will be passed, and hence, because of this, this is actually known as a high pass filter. Next will be on the band pass filter. Same signal here. They go through a band pass filter, okay, with a cutoff frequency. We call this a lower cutoff frequency of 15 kilohertz, a higher cutoff frequency at 25 kilohertz. Again, if I draw these two diagrams into one, okay, you can see very clearly that the one that will be able to pass will be just the 20 kilohertz. As you can see from here, the 10, 30, and 40 will be rejected. From here, you can see that I actually specified a band for the signal to pass. For example, for this case here, only 20 kilohertz will be able to pass. And hence, because of this, this is why this is known as band pass filter. Last but not least, again, by using the same four types of signal here, we actually go through the band reject or band stop filter. So basically, you can see that this band stop or band reject filter can have also two cutoff frequency. The lower cutoff frequency is at 15. The upper cutoff frequency is 25 kilohertz. Again, what I'm going to do is I'm going to put these two diagrams into one. And from here, okay, you can clearly see that this part here, which is the 20, will be the one that will be rejected. The rest will be able to pass. So hence, at the output of the band stop or band reject filter, okay, I actually specifically remove the 20 kilohertz signal, and the rest of the signal will be able to pass through the band stop or band reject filter. So from here, you can see that I specified which band to reject, and hence because of this, I call this as band stop or band reject filter. Okay, so from here, I hope you have a better idea on the different types of filter. In short, low pass, high pass, band pass, and band stop filter. Okay, so let me continue on the discussion. Okay, so in general, most RF and microwave filter, they actually consist of one or more couple resonator. Therefore, any technology used to create resonator can also be applied to fabricate filter. The unload quality factor of the resonator typically determine the filter achievable selectivity. Generalized filter theory operate on the principle of a resonant frequency and coupling coefficient of couple resonator in a microwave filter. Okay, so the rest of my discussion on the filter, under the playlist, I actually will discuss how to design low pass, high pass, band pass, and band stop filter on a microstrip line. Okay, beside microstrip line, there are also various forms to design the filter. The first one will be the lump element, okay, which I think that this so-called form of design can only work at low frequency. I will say more or less this form already face up, but this is a very easy concept. Again, I have done a video to explain how can we actually design a LC filter. Next will be the planar filter, which means that under microstrip, for example, which is highly utilized. So in fact, this is one of the cheapest, one of the easiest way to fabricate the filter. We also have coaxial filter, cavity filter, which I'm going to explain later on, dielectric, electroacoustic filter, and last but not least, this actually allow us to tune easily, which is known as the energy tuning base filter. So let's take a close look on all these different types of filter. So let's start off by understand the lump element LC filter. The simplest resonance structure that we actually use in RF and microwave in the LC10 circuit. So basically this is we always call the LC, which either can be parallel resonator or series resonator. Parallel means that either the L and C, they are actually in a parallel format, or the L and C, they are actually in a series format. So therefore, we call this as series resonator. When L and C, they are in parallel, we call this as a parallel resonator. So this circuit, they are actually very compact. But because of the low component Q or low quality factor from the resonator, this actually result in a very relative poor performance. Lump element LC, they actually operate in a specific band, which means that they need to work under this we call the upper and lower frequency limit. At very low frequency, which means that frequency can be from kilohertz to hertz. The size of the inductor required for the 10 circuit become too large, and it become not possible, not feasible to design this LC. So to address this issue, very low frequency filter actually designed using crystal. While at higher frequency, which is above 600 megahertz, the inductor in the 10 circuit become too small to be practical. We can't find this small inductor. And this is because the electrical reactance of an inductors with a given inductors actually increase linearly with frequency. So hence, at high frequency, achieving the same reactance will require an impractical low inductor value. Okay, so basically from here you can see the issue of LC filter. Basically, the frequency can only work at a specific band, cannot be too low, cannot be too high because of the inductor value. Okay, so let's move on to the planar filter, or we call this as a distribute element filter. Okay, so planar transmission line such as microstrip, CPW, coplanar waveguide, or maybe coplanar strip line. Okay, so basically they are actually very effective in creating filter. Okay, so as I mentioned earlier on, okay, the later part of the discussion on the filter design, I actually mainly focus on designing the filters on microstrip line. However, you can also apply to CPW or CPS. Okay, the process used to manufacture microstrip circuit are actually very similar to those employed in the production of PCB. Okay, so basically how you actually design the filter is very much the same as PCB. So because of this, this is very simple. Okay, you can see that this is very simple, and then therefore there are lots of advantages when we actually do in a planar filter design. Precision planar filter are typically manufactured using a thin film process. Higher Q factor can be achieved by employing low loss tangent dielectric material for the substrate. Okay, so basically this is for example a Roger board. Okay, by having a very low loss tangent dielectric, okay, basically can be as a substrate here. So this diagram here show all the different possible way to design filter. Okay, so basically the later part of the video, okay, I will actually discuss how can we actually design filter, okay, either the low pass, high pass, band pass, or band stop based on this form of configuration. Okay, let's move on. Okay, on the coaxial filter, okay, coaxial transmission line actually provide a very high Q than the planar transmission line. Hence, this make them very ideal for application that require higher performance. Additionally, okay, this coaxial resonator may use high dielectric constant, okay, to reduce their overall size. So basically, if you want to have a higher performance, you can consider to use this coaxial filter. The cavity filter, okay, cavity filter is still widely used. Okay, basically they work so-called at a lower frequency, okay, which is from 40 megahertz to 960 megahertz. Okay, they are well-constructed cavity filter. Okay, basically they can achieve high selectivity, okay, which means that very narrow band and a high Q, okay, along with improved performance stability at closely spaced frequency, okay, that can be achieved by increasing the internal volume of the filter cavity, okay, which means that you're going to put more. Okay, so basically this will affect, okay, the design here. In the microwave range, okay, so basically this is the microwave frequency, okay, at least above 1 gigahertz. Cavity filter become more practical in terms of size and offer a significant higher quality factor than lump element resonator filter. Okay, so when you actually move to a higher frequency, okay, the size of this cavity filter actually reduce, and because of this, okay, the size become more reasonable, the weight also become more reasonable. Okay, so basically this is the use case of the cavity filter. Okay, so let's move on the dielectric filter. Okay, dielectric filter actually made from various dielectric material that can be also used to create resonator. Okay, as with coaxial resonator, high dielectric constant material can actually reduce the overall size of the filter. Okay, when paired with low loss dielectric material, this filter can offer significant better performance than the other technology that we actually previously discussed. Okay, so basically this is also a very popular way to design a filter. Okay, so this is good when we actually need to tune. Okay, so this is what we call a energy tunneling based filter. Okay, so these are a new class of highly tunable microwave filter. Okay, this special filter can be implemented on waveguide, SIW, or low-cost PCB technology. Okay, they can be tuned to either lower or higher frequency with the help of switch insert at a appropriate position, achieving a board tuning range. So basically, this is mainly to tune the frequency. Okay, so if you need to tune the frequency, you probably need to design under this energy tunneling based filter. Okay, let's move on, okay, to the electroacoustic filter. Okay, so electroacoustic resonator actually based on piezoelectric material. They can be used as filter. Okay, since the acoustic wavelength at a given frequency is several order of magnitude shorter than the electrical wavelength. Okay, so therefore this electroacoustics resonator, they are actually much smaller and therefore much smaller, the weight also reduced, okay, as compared to our microwave counterpart, okay, such as the cavity resonator. A common example of an electroacoustic resonator is the quartz resonator, okay, which is essentially a cut of piezoelectronics crystal crammed between a pair of electrodes. Okay, this technology is typically limited to frequency in tens of megahertz. For microwave frequency in general above 100 megahertz, most filters actually utilize this thin film technology, such as surface acoustic SAW, okay, which I think you know, okay, and also the thin film bulk acoustic resonator, okay, which is the FBAR or TFBAR based structure. Okay, so basically this will be under the electroacoustic filter. Okay, so the last one which I'm going to go through will be the waveguide filter. Okay, so how does the waveguide look? Basically, this is how the waveguide filter actually look like. Okay, so a waveguide filter is an electronics filter constructed using waveguide technology. Okay, waveguides are actually hollow metal conduct designed to transmit electromagnetic wave. Waveguide filters are particularly useful in the microwave frequency band where their size is convenient and their signal loss is minimum. Okay, example of waveguide filter application can include the satellite communication, telephone network, and also the television broadcast. Okay, so basically because of the microwave, okay, so therefore the waveguide filter becomes smaller. Okay, you can design the waveguide as you can see from here. Okay, so basically with this, I like to end my discussion. Over here, firstly, I have introduced the different types of filter from low pass, high pass, band pass, and band stop. And then next, I give you an example and followed by these different types of filter. Okay, so with this, that's all I have for you for today. Once again, thank you so much for strong support. I hope to see you guys soon. Bye for now. Thank you.